Let me first introduce Professor Marlan Scully. Professor Scully is well known to us, not just because of his famous textbook with Suhail Zubari, but he is also a major figure in the quantum optics scene, both in America and worldwide. He has contributed a lot to the quantum optics scenes in the world, and in fact, he has visited Singapore at least once, several times. The last time he came was in celebration of Julian Swingle, and with Julian Swingle's centenary when we celebrate Julian Swingle's 100th anniversary. I believe most of you would know of his work, and he's certainly very well known in quantum information and computation as well. So without much further ado, let me pass on the stage, not really, the platform to Professor Scully, who will give us this interesting talk on the COVID. Thank you.
So actually, the talk that I would like to give is based on several aspects of work that we've been. The first half of the talk, I would like to focus on experiments that we've been doing using various aspects of laser Raman spectroscopy. And the second half will be relatively more speculative, more theoretical, based on the interplay between coherence and possible applications to biology. In the first instance, we're consistently using variations on Raman, which I'm sure you know about, but on the off chance that there are some graduate students who don't, I would like to take a few minutes to go over some of our earlier work involving coherent anti-Stokes Raman scattering cars. As you know, the problem presented itself 20 years ago of detecting anthrax in the mail. In Princeton, New Jersey, there was an onslaught of many murders by weaponized anthrax. Anthrax can be detected by wet chemical techniques, but it takes a while, and you're much better off if you could somehow use Raman spectroscopy, and that's what we do. So perhaps you know that the Bacillus anthracis bacterium is the origin of the endospores, which are, of course, weaponized. 10 to the 4 spores in a clump is a lethal inhalation. Less than that, the body can fight it off. There is at the center of the endospore a special chemical, dipicolinic acid. The weight, 17% by weight of that acid is in the center of the spore, and that you can detect by Raman. But of course, Raman is very weak. Roughly 1 photon in 10 to the 10 is converted from the incident laser to Stokes, downshifted, redshifted. And that means that it takes about 5 minutes to take a sample of 10 to the, say, 10 spores and get a discernible signal. So we're able to beat that rap by using coherence. And in particular, it's important that we have a new technique, not just coherent Raman, but femtosecond adaptive spectroscopic techniques, fast cars. This view graph made up by one of our students, Dmitry Pestov, and in particular, I'd like to remind you of the historical fact that the Raman effect was first predicted by Schmeckel in Austria, even before quantum mechanics. He was using the Heisenberg-Kramers relationships of producing the index of refraction, and his work was followed by experiments by Raman and other heroes, Mandelstam and Landsberg in Russia. The point being that you can think of a molecule, please, as a heavy anchor, oxygen, and a light mirror, say carbon, so that when you send light in at frequency nu, it's backscattered at the downshifted and Stokes and upshifted anti-Stokes lines. And that's the important technique that can be and should be understood as a quantum mechanical superposition of the molecule in the ground state and first vibrational excited state. So if at t equals 0, we have a wave function like this in terms of the coordinates of the nuclei, the two nuclei of here carbon and oxygen. We have a time-dependent excited state, a ground state with no time dependence. So at t equals 0, let's say we have the first Hermite polynomial and the ground state, add them together, and we have a compression of the probability of finding the system with a certain elongation, capital R. Half a cycle later, when t is equal to pi over omega, get a minus sign coming in to work for you, and the probability builds up on the right-hand side. So now the spring is expanded. This business of incoherent Raman, ordinary spontaneous emission type physics, is depicted on this view graph. And as we look at the incident pump and the emitted Stokes, we describe that by a Raman Hamiltonian, which can be derived several ways, but it's intuitively quite appealing to write it in terms of the annihilation operator of the pump, the creation operator for the Stokes, and then the flip from C to B if we're going from the ground state up, ending up in the excited state, we create a Stokes photon, and this whole process is described by the interaction Hamiltonian with coupling strength capital G. The wave vector of the pump and Stokes photon come into the game with R sub j being the position of the jth molecule in our ensemble. So now I'm going to use this Hamiltonian to calculate the so-called coherent process. Think, if you will, of a laser coming in at frequency nu1 and another laser at just the right frequency so as to be resonant with this ground state combination. This puts the molecule into oscillation, and now the light is injected either finding the molecule in the ground state and coherently emitting the Stokes photon, or vice versa. We can start in the excited state and we get an anti-Stokes photon. So that we can go through a little bit of algebra, which I will skip because it is not particularly educational, but you can calculate very quickly using the Heisenberg picture and this interaction Hamiltonian that was on the previous view graph, the expression for the operator corresponding to the Stokes radiation. And when you do that, and plug that expression into the number operator, A dagger A for the Stokes radiation, you get an expression of the form that we see here, and in particular, the cooperative coherent emission is proportional to the off-diagonal elements of the radiation density, of the molecular density matrix. Okay, so the ordinary Raman, of the type that Raman saw 100 years ago, is a spontaneous emission event, and it's very weak. Whereas the coherent Raman is proportional to, among other things, the number of molecules, N molecules, not N atoms. And here we see that there are two contributions then, the coherent and incoherent. The ratio of these two is indicated in the box. And so here we see something interesting. The ratio of coherent to incoherent emission is proportional to the number density of molecules times the wavelength of the Stokes light squared times the size of the cloud containing the molecules of interest. All of that multiplied by the coherence factor. And when we go to the lab and do the experiment, we find indeed that the ordinary Raman, very weak, 1 photon in 10 to the 10, is enhanced by many orders of magnitude. Here we see some 6 orders of magnitude, 4, 5, 6 orders of magnitude. And in other experiments, we have even more. So this is the name of the game. And you must be able to get around the fact that all the molecules in the ensemble are oscillating at the driving frequency. So as we indicated in the first view graph of our science article, the driven system is here, let's say we're looking at CO and we're tuned to be resonant. And so we will see the light scattered, which is number 4, the anti-Stokes light. But for some other molecule like SO, we will also see the same frequency because the molecules are all oscillating with the driving frequency, the frequency difference between the radiation 1 and 2. So this is the bad news about coherent Raman spectroscopy. Too much background noise. The good news is that the signal is bigger. The background noise is bigger too. So what you want to do is to turn on the pump and Stokes and then turn it off, turn those driving fields off and turn on a probe, which is very sharp in frequency. And you'll now find a signal, which is indicated here, is a femtosecond adaptive signal, and it's very sharp compared to the CARS signal. And that's what we have been using for the last decade and more, first for anthrax and then for many other applications. Now, if you combined this technique with surface enhanced Raman, you can get, as our friends here indicate in their nice review article, an astonishing sensitivity. Indeed, Alexei Sokolov here at Texas Atomic and Molecular University and others were able to show a enhancement of 7 orders of magnitude beyond what you would normally get without doing a surface enhanced type of technique. Now, I won't go into the surface enhancement except to say that when you come in a moment to the utilization of atomic force microscopy and a tip, you'll see the payoff more clearly, and that's indicated here. Volker Decker from Jena, an expert in this kind of variation hybrid Raman, did a very nice experiment and a series of measurements in which he puts a tip here and shines laser radiation in on the tip. The tip has a curvature of about 50 nanometers, the light wavelength 500 nanometers. But Mother Nature is kind to us for a change. And because of the structure on the tip, you're able to trace out the amino acid content actually as indicated here. Now, as Volker pointed out, we're using an enhanced fast cars technique, faster cars. And that technique is indeed very powerful, enables us to study one COVID-19 virus and other viruses, and you can tell the difference because of the Raman spectra. So this is the virus corresponding to the Spanish influenza virus, the spectrum corresponding to the Spanish influenza, and here we have the E. coli phage virus, and you can see the spectrum of the two is very different. And this sort of technique is being applied by Professor Yi here at Texas A&M and co-workers to study a variety of problems within the context of molecular physics. For example, we can now read out the RNA nucleotide sequence. And we're doing this, remember, with a tip that's tens of nanometers, maybe 20, 40 nanometers in size. And we're measuring, sensing the difference between the nucleic acids, which are spaced by half a nanometer, a really magnificent accomplishment. And the guy who really deserves most credit for this is Dr. He, one of our recent graduates who's now gone on to a postdoc at Caltech. So that first part of my seminar, I'd like to conclude. And so Ni's article got the cover of the American Chemical Society Photonics magazine. This is pollen season here, unfortunately for me. So now I'd like to shift gears and talk about a problem that Roger Penrose of black hole fame gave us in his book entitled The Emperor's Mind. You remember that he talked about the possibility and the utility of having quantum mechanical effects in the mind, and that was a interesting, if somewhat far-fetched, far-reaching suggestion. But recently, we've gone on to apply these ideas of superradiance and coherence with some success in providing a basis for Penrose's interesting idea. It really begins with Freud. Remember, Freud had a hypothesis that we would have a kind of cooperative phenomenon in proteins associated with vibration of the molecule, and that this would, in many ways, be related to Bose condensation or indeed laser systems. Now, the condensation of N bosons is much like a laser, and we are using these ideas together with Professor Zhang of Hong Kong and Girish Agarwal, who's joined us here at Texas A&M. So I'll save my voice maybe and let you read this. But the important point is that this business of Freilich's cooperative phenomenon is very like a laser, and the same equations that describe the photon dynamics of the laser can be used to describe the Freilich effect. And with that, and trying to conserve my voice, I'm going to switch on to quantum coherence in brain microtubules as a follow-on to the Penrose suggestion. One point of view has it that the quantum mechanical phenomena that might show a kind of condensation with minimized noise could perhaps take place inside these microtubules, which are ubiquitous in living systems. And perhaps this, they suggested, might shelter the signal and provide a mechanism for a kind of cavity quantum electrodynamics in the sense of Rausch and Walter. So that was one suggestion that began to lend substance to Penrose's idea. And beyond that, a perhaps more interesting suggestion was made a couple decades ago that superradiance could perhaps play a part in this kind of coherent phenomenon functioning as they like to think of it in the brain, but functioning in any context between neurons, perhaps in the body someplace else, would be equally fascinating. And so I'd like to make that point. And looking forward here, a interesting paper came up a year or two ago by colleagues in Spain and in Mexico. They suggested that superradiance could be taking place in these microtubules. That requires some explanation. So this is their point of view. First of all, please remember that Dicke superradiance causes the atoms in a given locale to decay much faster, essentially n times faster than a given atom in free space. So that in this context, suppose we have one spiral and maybe some 10, 15 atoms in that spiral. And then what these guys did is to calculate the rate of decay of an excitation, essentially a photon tied to the microtubule. The rate of decay is n times faster than gamma, where gamma is the free molecule decay rate. Now here we're plotting the Lamb-shifted frequency of the individual radiating constituents. If you will, please think with us about the fact that the imaginary part of the decay is what gives us Wigner-Weisskopf results. The real part shifts the frequency splitting. That's the Lamb shift. So this is a cooperative Lamb shift. And to talk about the cooperative superradiance, we have to take into account both the fact that the radiation is shifted in frequency and it is emitted more rapidly. So that kind of logic is applied by our friends here in an interesting paper, and they see that there are modes which are decaying very rapidly, and indeed, when you take not just one spiral, but 10 spirals, you get a factor of roughly 10 increase in the decay rate as indicated here. Now, this is something that we were very interested in when we saw this paper, because we had been working on Dicke's superradiance from the point of view of trying to see new interesting phenomenon and perhaps new interesting applications of the Dicke problem. And what we had been doing was analytical, whereas what they're doing in their nice work is numerical. And if we look at what we've been doing, my colleague, Professor Swieczynski, and I have been thinking about a different kind of Dicke state. But first, let me think with you about the superposition of atoms in some ensemble, in atoms. And let's first think about Dicke's problem. He was looking at nuclear magnetic resonance. Wavelength is hundreds of meters, and the size of the sample is a couple centimeters. So all the atoms in this game, from Dicke's point of view, were at the same point, and they added coherently, cooperatively is a better word. Now, if on the other hand, the atoms are spread out, and we can think of them as being spread out in a line or in some configuration, think of them as being along a line, one dimension, then you're going to have factors coming in corresponding to the excitation that we have in mind. So let's imagine that we have one photon coming in, exciting this cloud, but we don't know which molecule is excited, or which atom in this case. We excite this ensemble, and the state which is prepared by this extended grouping of molecules has these factors R1, R2, up to Rn in it. And so we have the first spin up and the last spin up could be. We don't know which. So it's a coherent superposition of such a ensemble. Now we call it a timed Dicke state because indeed, if I multiply and divide by the speed of light, I get a frequency, times a time corresponding to the passage time of light from, say, the near edge all the way into some point in the medium. So these are really time, frequency times time factors. And so we call it the time Dicke state. And we find that the radiation corresponding to an ensemble of such atoms send in a pulse and now watch the radiation. It will come out predominantly in the same direction. This is a log scale. So it's overwhelmingly going in the same direction and decays much faster than an individual molecule. So that's time Dicke superradiance. And in this game, the wavelength is small compared to the size of the sample. It might be 10 to the 4 oscillations of light as we pass our pulse through this sample. Now, in this kind of configuration, we have the light propagating in the forward direction, and because of the sequence of atoms being prepared with these factors, it's more or less what you would expect. Now, let's go to a different problem. Let's imagine that we have the size of our little gas cloud to be very large compared to the Wigner-Weisskopf decay rate times the time t, okay? So that all the light is inside this ensemble, whereas here, the decay rate is large. The decay of the system produces a pulse which is large compared with the sample. What we find is that then the probability of finding one atom excited, or indeed a single photon trapped in this cloud or contained in this cloud, is something which rings in time and decays with a rate which is governed by the frequency rate, frequency leakage out of the cloud. That reminds you of the opposite problem in which you have not n atoms, but one atom. This is one atom in a cavity containing n photons, and the exact same thing happens. Here I'm now looking at the probability that the atom is excited, and consequently that one photon was absorbed, and we see this kind of ringing, and the decay rate is governed by the Q of the cavity. So here is an interesting kind of interplay between cooperative emission of n atoms and one photon and the coherent laser-like phenomenon associated with one atom and n photons. This is stimulated emission, and this is spontaneous emission. Spontaneous, but correlated. Every atom is correlated to every other atom. So there is a mini particle macroscopic coherence involved, but it's really spontaneous emission, not stimulated emission. Well, that's very interesting, and it's something which you can read about in the literature of the last decade. But we found also that the Lamb shift of this n atom ensemble comes into the game and can indeed give you a noise term, so to speak, and rub out this interesting effect. So that's the good news. Good news is there's some interesting physics here, thanks to Dicke in a timed Dicke configuration. The bad news is that you seem to lose this effect due to vacuum fluctuations and the many atom lamp shift. But now there's more. If you see, before, I'm going to tell you in a few minutes that by having a cloud of these atoms prepared in a particular configuration, you can get around this lamp shift problem. But before I do that, let me back up and say, okay, this is the N photon compared to the N atom problem. Now let's keep that in mind and look at this next view graph, in which we see that as on the previous view graph, we have oscillation of excitation of our single atom being excited or single photon being emitted. Now, this stimulated emission, single atom maser type physics is, as we've noted, is very analogous to the single photon superradiance. And there is a kind of quantum amplification that can take place in the context of this superradiance, and that we would love to talk about, but that's the subject of another seminar. Now I'd like to ask you to compare something you know very well, namely the Rabi oscillation rate corresponding to the flopping back and forth between the excited state and the ground state. And oh, by the way, I have to tell you, Rabi used to come to MIT back in the days, and we would all enjoy his wit. One day we were telling him about Rabi oscillations, and he said, "Rabi oscillations? What are Rabi oscillations?" So of course he knew. We explained it to him, and in that case we were talking about Rabi oscillations of Josephson junction systems. And we said, aren't you embarrassed that now we can get high precision without using atoms in their requisite precision? And he said, oh, why should God be the only one who can make an atom? So here we have the results of an atom oscillating between the state with a matrix element coupling the excited and ground state, P divided by h bar times the square root, the ubiquitous electric field per photon, the energy of the photon h bar times nu divided by epsilon 0 MKS units times the volume of the cavity times, of course, the square root of the number of photons times the time. So that's the typical single atom maser type result. V, I emphasize, is the photonic volume, and N is the number of photons in the cavity. Here's what we find if we work that same problem, the same kind of problem, that is to say, as indicated here, we find that the probability of our single photon being emitted looks exactly the same, except that the volume of the cavity is replaced by the volume of the atomic cloud. And the number of photons is replaced by the number of atoms. A very interesting and I think a beautiful result. But now I'd like to go back to this question of the eigenvalues associated with decay and the frequency of the atomic two-level system. So we solve for the decay rate, and we find that the decay rate for a shell of atoms, put them on a shell, like in the microtubules that our friends were doing in the first view graph. Let's go back to that just to keep it in our mind's eye. So they were thinking of all the molecules here being on a surface. Great, that's what we want to do. And indeed, what we find is that when we look for this kind of timed Dicke superradiance and put all the atoms on the surface of a shell, we get this same kind of result that they got, except that now it's described by an analytical expression. The Bessel function description of this phenomenon gives us a decay rate, which for our problem with 200 atoms is very like what they found. And in the context of this particular example, the cylinder, we see a very pretty kind of correspondence between what we have here, analytical, and what they had in their more complicated, more realistic problem of the molecules, each of which is radiating into the tubulin. So we have perhaps more support now for the idea that there could be superradiant coherent effects in the cavity. Maybe now, instead of the molecules decaying in microseconds, maybe they decay in femtoseconds or hundreds of picoseconds, or some time which is longer than typical diffusion times. The diffusion times of atoms in a atomic optical configuration is on the order of what? Picoseconds. Now, I say diffusion, I should be careful. I'm talking about phase diffusion, okay? Of course, all of our atoms are stationary. So this phase diffusion, T2 in the language of NMR, is something that takes place in a very well understood fashion, with the time on the order of fractions of a microsecond, say. But if we had everything taking place in very short times, short compared to this picosecond decay time, picosecond is too short to see microsecond pulse dynamics in any coherent form. But if we could get in with short pulses, as we think we might be able to, maybe there's something very interesting here. So the summary of this part of the talk is really showing how the study of two-dimensional molecular structures collectively emit light. And the bottom line is that this could be very useful in the context of coherence effects in biological systems and maybe even in quantum informatics. So with that, my talk is running out at the same time my voice is running out. So I'll thank you for your attention and patience and stop there.
Right, thank you very much. So we can show a sign of applause. Any questions?
Yeah, I do have a question. So first of all, thank you very much for this wonderful talk, and especially at this time of the day in your time zone. I know it's quite late, so thank you very much. I had a question about the detection method with the tip, and I was wondering how would that be deployed in the field? How would you bring the samples under the tip? Is that something that needs to be prepared, or is that something where you just blow your sample in and you get some kind of results? How would this kind of be?
Right, right, good question. excellent question. Let me phrase it this way. There are two, at least, ideas goals here. First, we'd like to be able to understand and to have some kind of insight into the actual virus itself. So we'd like to be able to trace out the nucleic acids on the surface. And this is the sort of thing that Volker Decker and his crew in Jena have been doing for the last 5 years or so. Jürgen Popp and Volker Decker, two heroes in this business. Now, what we were thinking of is, of course, following that interesting work and applying these techniques in different systems. But for example, first of all, looking at how we can read out a RNA sequence, single-strand DNA or RNA. But how could you use this, one might ask, to actually detect the presence of the COVID-19 disease? Well, you would envision using a tip-enhanced property, not so much as surface-enhanced. Okay, so if we have surfaces which are rough, and those we prepare perhaps with graphene, as some people have done, and we flow our sample containing the virus through this thicket of little graphene tubes, then we could, in principle, and in fact, in practice, in many ways, see an enhanced signal from a few of the virus particles being trapped in this kind of a surface that would give us a much stronger signal and not require that we localize the virus as well as we must, of course, to look at the surface of a single virus. So on the one hand, it's a great technique for learning more about the virus. On the other hand, not using tip-enhanced Raman so much as surface-enhanced Raman, there's a possibility that we could actually have a new probe looking for the presence of the disease.
Thank you.
Right. Any other questions? Professor Scully, for the your top view on these microtubules, the section on the microtubules, did they look at participation ratio or anything to that effect?
A what
Yes.
ratio?
Oh, sometimes participation ratio for these spirals.
Oh, okay. Now, in the microtubule problem, we were looking at ways in which we could see coherence effects, and we were nowhere able to get a useful technique to see a virus in a configuration that involved the microtubules. The tubules are like 25 nanometers in diameter, and the COVID-19 virus is up around 100 nanometers. But you might think that you could put the technology to work if you could break open some system and have perhaps a well-specified ensemble of molecules in this microtubule type cavity. So that's a possibility. Your idea is an interesting one, but right now we're trying to more do fundamental research with the microtubules and applied research with the tip-enhanced Raman.
Are there other questions? I think it's getting very late for Professor Scully. It's 11 p.m., right? And you're still in the office.
Yeah. Well, thank you for.
Thank you very much. Thank you very much for your kind acceptance to give such a wonderful talk. Yeah, if there are no, yeah, sorry. Yeah,
So we
if there,
invite you to Texas for the next meeting.
Yes, we will be pleased, in fact, to invite you to Singapore if there is no COVID.
Right on.
At the moment, travel is difficult, but otherwise, we will be happy to invite you to Singapore once again.
Beautiful Singapore is always a delight to visit. So
right.
I'll say goodnight.
Thank you very much. Yes.
Bye-bye.
Thank you.